Hello everyone. My name is Sudipta Sinha and I'm a research scientist at Microsoft working on computer vision. Today, I will talk about Azure FarmBeats and tell you how Microsoft is empowering farmers with tools for pursuing data-driven agriculture. According to the United Nations, by the year 2050, the world population is expected to increase to 9.8 billion. Food demand is estimated to be 60% higher than it is today, but the world's food production is not growing fast enough. Agriculture consumes a lot of resources and is responsible for greenhouse emissions as well. Therefore, it is important to find sustainable ways to improve agricultural productivity. One of the most promising approaches for improving crop yields in a sustainable manner is data-driven agriculture, also called precision agriculture. The idea is that a farmer uses a fine-grained precision map of the field to make decisions during the crop cycle. These precision maps may contain information about the distribution of attributes like soil temperature, moisture, pH levels, etc. across different locations on the field. This then allows the farmer to treat different parts of the field differently. However, the main hurdle to widespread adoption of precision agriculture is that a lot of sensors need to be deployed in the field, and this can get quite expensive. Azure FarmBeats is an end-to-end system for enabling data-driven agriculture. It is now publicly available as a service on our Azure cloud platform. The FarmBeats system builds upon technologies from four areas: wireless networking, sensor design, cloud and edge computing, and aerial imaging. I will briefly talk about sensors and networking and then focus mostly on aerial mapping for the rest of this talk. This is Andrew Nelson, who is a farmer in Washington State and a close partner of ours. Let's hear what he has to say about FarmBeats.
Farmers need a lot of tools to make better decisions. Any decision on a farm is really a big deal. Azure FarmBeats combines information from IoT devices, insights from machine learning, and serves it up in a way where other platforms are able to build off of it and help make a farmer more productive. The sensors measure temperature, wind, rain, humidity, soil moisture and soil temperature, CO2 levels, the solar intensity as well. One of the ways that the model can help make better decisions is temperature predictions. So that model will then tell you, oh, it's going to freeze tomorrow morning, and it's going to freeze, in the lower area. The whole field is not the same. So this year, when I have multiple sensors in one field, what I noticed was the soil profile on the top of the hill was different than on the bottom of the hill. And usually what we do is we plant the whole field the same. But it was so different that I seeded fewer plants up higher in the field and seeded more down lower. And then I could track it throughout the year with drone flights and with yield data at the end of the year.
So over the past few years, we have partnered with several farms based in the US and in India, and the FarmBeats system has been deployed at these sites where we've been running several pilot projects. Now, the first challenge that FarmBeats addresses is that of network connectivity. So farms are often located in remote areas where network coverage can be quite poor. Even when the farmer has an internet connection in their home, the field itself could be miles away, and this makes it quite challenging to connect the farm to the cloud. In FarmBeats, we solve this problem using a wireless networking technology called TV white spaces. We use TV white spaces to connect sensors on the farm to a base station on the farm, and then the base station to an edge computer in the farmer's home, where we assume that a slow internet connection is available. TV white spaces is a technology developed at Microsoft Research. It basically exploits unused TV spectrum to transfer data. This is particularly effective in remote areas because there are fewer TV channels and most of the spectrum is unused. So this makes it possible to transfer even high bandwidth data such as drone videos over TV white spaces. FarmBeats connects a wide variety of sensors on the farm to the cloud. Many of the sensors are on the ground and can be solar powered. They measure a variety of attributes such as soil temperature, moisture, pH, and other environmental factors such as wind speed and direction. Finally, we also use consumer drones to collect imagery on the farm, and most of my talk now will focus on how we process that imagery. Consumer drones are nowadays being used increasingly on agricultural sites. The technology has become reliable and affordable, and many of these drones are quite easy to fly. They can be flown autonomously based on a pre-programmed set of GPS waypoints. Here on the left is an example of a video from a downward-facing camera on a drone flying at about 50 feet above the ground. On the right is shown a high-resolution orthophoto, which is automatically generated by our system in about 30 minutes on a single machine. Drones can offer several advantages over satellites and aircrafts for collecting aerial imagery. First, they are quite inexpensive. Second, farmers can control the acquisition themselves and decide to collect data as often as necessary. Finally, data acquisition is less impacted by cloud cover and inclement weather. At the heart of our image stitching pipeline are a number of computer vision and aerial photogrammetry techniques that are now quite mature. First, we use visual feature matching to find pixel correspondences in overlapping drone images. Then we use structure from motion to recover a 3D surface reconstruction of the farm from hundreds or even thousands of overlapping images. Next, we project the images onto the reconstructed surface and use image stitching and compositing algorithms to create a seamless, high-resolution image. Here is an example of a gigapixel orthophoto stitched from 390 images of a wheat farm in Washington. This was captured around November last year. The area covered in the photograph is about 0.25 square miles, and each pixel roughly corresponds to a 3 centimeter by 3 centimeter patch on the ground. We were able to compute this image in about 40 minutes on an edge node. To give you an idea of the resolution, here I show a zoomed in section of a small part of the image. Notice here how clearly you can see even the tractor tracks on the soil. Here is another example of a high-resolution orthophoto generated by our system. In this case, the farmer was able to gain some interesting insights about the condition of the field and the location of the cattle. Our system can also stitch multispectral images. Here are example images stitched by our system from images captured on a drone. And these multispectral images are also registered to each other. So this sort of imagery can help the farmer monitor crop health and make important decisions during the crop cycle. At one of our farms in Washington, we also collected imagery on a weekly basis over a duration of 2 months. Here on the left are shown the 3D point clouds reconstructed from structure from motion from these weekly flights. And on the right is shown an aerial time lapse of the farm based on our stitched and aligned images. So this sort of 4D imagery can be quite useful for change detection and long-term analysis. For example, in this case, the farmer was able to monitor the region on the farm where the new crops were growing, and were able to also detect weeds growing in another part of the farm. In one of our earlier research projects, we also proposed a new technique to generate precision maps from aerial images. Our goal there was to combine measurements from a small number of ground sensors with the aerial imagery to regress a detailed precision map for the whole field. The main idea was to use visual features from the aerial image to make predictions about the target value, for example, soil moisture, as shown in the image on the right. Our model is trained and updated using a small number of geo-registered ground sensors, and the trained model is then used to predict the target value in the areas of the farm which do not have sensors. We have also explored low-cost alternatives to aerial imaging based on helium balloons instead of drones. In this setting, the images were captured by a smartphone that was mounted on the tethered balloon, and a person holding the tethered balloon walks around the field to capture the imagery. Even though the raw image quality is lower because the balloon is constantly spinning and moving in the wind, our imaging pipeline is still able to take such raw image data and produce accurate orthophotos from the footage, such as here is an example shown on the left. So in spite of a lot of progress that we've made, there are still some challenges that we face when mapping agricultural farms. Finding image matches between overlapping images can get quite difficult sometimes when we have a homogeneous crop texture. This is very common on industrial farms. Or sometimes it can be difficult to find correspondences between pixels when during windy conditions because the crops move in the wind. Matching images across time can also be challenging when the appearance of the field changes over time as the crop grows or when the weather changes drastically. We are also exploring machine learning-based solutions to problems that can take advantage of this sort of aerial data and then make predictions and solve problems like yield prediction or anomaly detection on the farm. So that's the end of my talk. I would like to acknowledge the efforts of several dedicated people who have made significant contributions to FarmBeats. Thank you for listening.